Good evening. Welcome you all to the sixth webinar hosted by the Civil Department Association Force of College of Engineering Patanapuram. Kindly raise your doubts regarding the topic in the YouTube comment section and we will be sharing it with Miss and she will clarify it at the end of this section. I'm glad to introduce the lecturer of this webinar, Dr. Surya. Let me give you details about the resource person. Dr. Surya is currently working as Assistant Professor in the Department of Civil Engineering, NSS College of Engineering, Palakkad. She has completed her doctoral degree in Geotechnical Engineering from IIT Madras. She secured her Masters in Environmental Geotechnics from NIT Calicut and Bachelor's in Civil Engineering from Mahatma Gandhi University. She has working experience with many of the sophisticated analytical instruments in material characterization and has experience in mathematical modeling. She has carried out consultancy works from various organizations and projects financially supported by external sponsoring agencies like CARD. So now let me welcome Miss to this webinar. Welcome Miss.
Hello.
Madam,
Okay. A very good evening to one and all. Thank you, Rajalakshmi, for the nice introduction. As part of the Ceasidle seminar series, I'd like to talk about the topic, the characterization of geomaterials. So I hope most of the audience in this webinar is BTech students. So I thought I'll just brief you some of the common experiments and one research work which I was working with during my doctoral program as part of this webinar. So as Rajalakshmi explained, this is my profile. This slide shows the overview of my presentation. So during this presentation, I'll be discussing about what is a geomaterial, what is characterization means, what are the common tools and techniques used for characterization, and one of the characterization which I have adopted during my work, that is thermal characterization. And in addition, I'll be introducing some of the research areas in geo-environmental engineering. So why I am focusing more on geo-environmental engineering is that it is one of the recent advancements in civil engineering. So it is a part of geotechnical engineering, and we can precisely tell that it's a mixture of geotechnical engineering and environmental engineering. So now let us look what is a geomaterial. Geomaterials are the materials influenced by the geological systems originating from the long history of Earth. So these can be primary or secondary raw materials. The only thing is that these will be mainly mineral-based materials. Examples for naturally occurring geomaterials are rocks, sediments, and our soils. So in this era of industrialization, as everything have a duplicate one, these materials are also artificially produced to the output as construction materials or the byproduct waste. Example for such refined, processed, or manufactured and recycled materials are cement, concrete, slag, fly ash, etc. Now, what is characterization? Characterization refers to the broad and general process by which a material structure and properties are probed and measured. It is a fundamental process in the field of material science, without which no scientific understanding of each material could be ascertained. And characterization will be characterizing the material for its structure, its properties, performance, and processing, depending on the application areas. So there are several tools and techniques involved in characterization of materials. We'll see what are the different characterization techniques which we will be using mainly in geo-environmental engineering. So as I discussed already, the composition and structure of every material govern the behavior of that material. So the structure and composition of the materials can be investigated using microstructural studies or spectroscopic studies or even both. Common microstructural studies used in civil engineering are SEM and TEM. SEM is a scanning electron microscope and TEM is transmission electron microscope. The working principle of both are same, but the only difference is in their resolution range. SEM is a type of electron microscope that produces images of a sample by scanning the surface with a focused beam of electrons. The electrons will interact with the atoms in the sample, producing various signals that contain information about the surface topography, and from that, we'll get to know the composition of that sample. Whereas a transmission electron microscope mainly focused on very small specimens. So, here a set of accelerated beam of electrons will be passing through very thin specimens that enable us to observe the features like structure and morphology of the material. So these are some of the this an image obtained for sodium bentonite, which is a type of clay mineral. I hope you might have heard about different clay minerals. So the first one is SEM image. As you can see, in SEM we can go up to micro levels, whereas in TM we'll get more detailed picture, which is at nano level. And a major spectroscopic technique which used to identify the structure of a material is X-ray diffraction. X-ray diffraction is a rapid analytical technique used to identify the structure of material. It used for phase identification of a crystalline material and can provide information on unit cell dimensions. So here, rather than thin samples, the samples will be in powder form. So this powder diffraction is commonly used to identify the unknown substances by comparing the diffraction data, which will be mainly in the form of a graph, which connects the relative intensity and 2 theta angle, and it will then compare the data with the database available, that is called as ICDD, International Center for Diffraction Data, and from that we'll get to know the mineral composition of that material. So in the right hand side you can see this is an example for XRD obtained for sand and sodium bentonite. So this XRD works based on Bragg's law, which relates the lambda value, that is the wavelength of a X-ray, and the incident angle 2 theta. So this will be related, and accordingly mineral composition will be identified. Other than this, there are many other microscopic and spectroscopic techniques, which I have discussed was the most common one, which will be generally used. Next, we'll see what are the techniques for the determination of the material properties. So for material properties, most importantly, we'll be finding out specific gravity, grain size distribution, Atterberg limits, if the material is clay soil or fine grain soils, and relative density if granular materials are of our concern. So coming to specific gravity, you all will be aware how specific gravity we will be using, measuring in the laboratory using a pycnometer for granular materials and specific gravity bottle for fine grain materials like clay, fly ash, slag, etc. So the third figure is a gas pycnometer, which directly measures the specific gravity of solid substances using helium gas. The advantage of helium gas pycnometer is that since a helium gas is very inert and lighter, it will give more accurate values of specific gravity of substances. Next major property is grain size distribution. We used to measure the grain size distribution using sieve analysis and sedimentation analysis. Again, sedimentation analysis using pipette or hydrometer analysis. And finally, the total grain size distribution curve will be obtained by combining the results of both sieve and sedimentation analysis. Next is the consistency indices. If our geomaterial contains more of clay materials, we have to go with the consistency limits because clay soils behave different with different water contents. So accordingly, we have 3 limits: liquid limit, plastic limit, and shrinkage limit. So liquid limit we used to find out using Casagrande apparatus or cone penetration method, and plastic limit will be preparing 3 thread and finding out the water content, and shrinkage limit using shrinkage limit apparatus. Now, the common geotechnical test which we'll be using is compaction, hydraulic conductivity, shear strength, etc. Usually, we'll be compacting and using the soil for different applications. For example, like subgrades, mud wall constructions, etc. So, for those applications, compaction will be very important. So, compaction, the conventional testing method is Proctor compaction test. However, since this Proctor compaction testing is very tedious, uh, Sridharan and Shivapullaya, two scientists from IIC Bangalore, have developed a miniature compaction apparatus. It uses a scaled down compaction testing apparatus, and the compaction effort has also reduced. So we can use this one if we have a lot of samples to be compacted. Now, next is the hydraulic conductive. Uh, from the compaction, when it is important is mainly for the subgrade purposes. So, from the compaction characteristic curve, which is a result of compaction, we'll come to know at which water content, at what density we have to compact our material in the field. So, in this graph, you can see we can divide the compaction characteristic curve into two. On the left hand side, you'll get dry of optimum, and right hand side will say wet of optimum side. So, on the left hand side, since it is dry, the structure will be more flocculated. So, those materials which are compacted on the dry of optimum will be characterized with high permeability. And on the wet side of optimum, if you are compacting, we'll get lower permeable materials. We'll be getting more strength on when we reach at the optimum moisture content side. Next experiment is a permeability test. The conventional testing is constant head or falling head permeability testing apparatus. And one of the recent testing for permeability is a flexible wall permeometer. The advantage of this is we can ensure proper saturation of the sample, and since we are using flexible wall, there won't be any side leakage. Third geotechnical property which we used to do is consolidation testing. So this testing we won't be doing usually. This testing is preferred when required when the application of the our material is in embankment construction, or when we are expecting any consolidation settlement in the study area. So for that we used to do conventional oedometer testing or digitalized oedometer testing to get the consolidation results. And another important geotechnical property to be tested is a shear strength test. So, shear strength characteristic will be most accurately measured using triaxial testing. But however, in most of the work, we won't be go for triaxial testing since it takes more time. So, we used to do unconfined compressive testing if our soil is having cohesive nature. Now, being discussed about the common test and characteristics, these are the common generally used test and characteristics. And depending on our study area, we can then go for some other characteristic studies. So, let me discuss now one important characteristic that governs the behavior of a geomaterial when its application is in buffer material for nuclear waste management. Because of the ever increasing energy demand, we are using nuclear energy for huge electricity production. However, the main challenge in this era is that how to dispose this nuclear waste or how to manage this waste. This nuclear waste can be generally categorized into three depending on their when their radioactivity dies down. They are low level waste, intermediate level waste, and high level waste LLW, ILW, and HLW. And in general, there are three principles for waste management. Either we can dilute and disperse the waste, or concentrate and contain, or delay and decay. The disposal of first two categories, that is low level and intermediate level waste, are disposed in a simple manner by preparing concrete trenches at shallow depths, which are called as NSDFs, near surface disposal facilities. But due to the presence of long lasting radioactive transmutation reactions, high level waste can't be subjected to similar disposal practice. Because of the hazardous nature, these wastes are first calcinated and vitrified using borosilicate glasses, then sealed in stainless steel containers, which are called as canisters, and then we will be buried them into deep geological formations called as DGR or deep geological repositories. The whole DGR involves the process like an access tunnel will be dug at a depth of 500 to 1 kilometer below the ground surface. The trenches will be dug out to place the vitrified canisters safely. And once the canisters are safely placed on the trenches, the trench and access tunnel will be closed with the help of buffer and backfill materials. So, this disposal practice is considered to be the best option to isolate the radioactive waste from the surrounding geoenvironment for few thousands of years. So, by that time, the radioactivity may dies down and then the waste will be non hazardous. The safety of this repository is attained by placing these barriers around the radioactive canisters in order to restrict the release of hazardous radionuclides to the geoenvironment. So, the long term performance of this canister depends on the efficiency of this buffer and backfill materials. So, in order to demonstrate a safe containment of waste in deep geological repository with no impact on the environment, proper characterization of buffer materials is of primary importance. So, the efficiency of this DGR can be evaluated by long-term performance of the buffer material under combined influence of several factors like physical, chemical, and thermal loadings under adverse saline environments. So, first of all, while characterizing buffer material, we need to know how the temperature of the canister, because even though it is a nuclear waste, its emission reactions will be carrying out. Maybe it will be at the final stage. So, these will be characterized with high temperature because of the exothermic nuclear emission reactions. So, we need to know how this temperature is migrating through the buffer materials. So, this can be analyzed by knowing its thermal conductivity, which has an impact on the maximum thermal load that can be applied to the canister. So, for that, a methodology was developed to find out the thermal conductivity of buffer material using a thermal needle probe. A thermal needle probe, before going into the thermal characterization, let me show you what are the basic characteristics which I have obtained for my studied material. So usually, generally, we'll use clay as a barrier or liner material, but the problem with clay is when it comes at high temperature, desiccation cracking can occur. So in that case, we'll be mixing this clay with sand or silt, and then we'll restrict this desiccation cracking. So for this study, I have considered sodium bentonite and so this table shows the physical properties and consistency indices I have obtained for the materials. So if you want, you can get the grain size distribution and soil classification as per the US classification system will be good for your work. So I could find that my clay is highly compressible clay with a high liquid limit of 364, which tells me that it is a highly reactive bentonite. And this figure shows the grain size distribution curve. So since I have used fine grain sand, only one range of sand particles I have selected. So you can see that this kind of curve you are getting. And this is the X-ray diffraction pattern, which I have already shown before. And this is the compaction result. So since, as I told, we'll be mixing bentonite and sand, I have to try different weight proportions of sand and bentonite. So accordingly, I have named like SB10 means sand bentonite mixture with 10% of bentonite content according to the weight. So for different sand bentonite mixtures, I have conducted compaction test. I did both standard proctor as well as miniature compaction testing, and I could observe that both the results are matching. And also, I have conducted hydraulic conductivity testing. So from the hydraulic conductivity results, I could ensure that it is within the range of 10 power minus 10 meter per second. That means it's very less. Hydraulic conductivity is very less. So I can ensure that there will not be any water movement or any liquid particles will be permeating through my buffer material. Now, coming to the thermal properties, I have told we have developed a thermal needle probe in the laboratory. This thermal needle probe was working under the principle of transient heating technique. Transient heating technique states that the rate of temperature of heated body, that is delta T, is proportional to the thermal conductivity of the material. The thermal conductivity is denoted as K, capital K. So the rate of temperature of the heated body is proportional to the thermal conductivity of the material in which it is embedded. So in this method, heating element was considered to be assumed to be a straight line of infinite length and infinitely smaller diameter embedded in a homogeneous and isotropic material of infinite extent. So I have taken some of the assumptions, like I have assumed my material is homogeneous and isotropic. So the change in temperature, that is delta T, I can connect it to the uh, thermal conductivity using this equation. So from this equation, if I can plot the variation of delta T with log T2 by T1, T2 by T1 is the time. So at different time intervals, if I can get the delta T value and I can plot a variation, I'll get a straight line because it is a straight line equation. So the slope of that will give me Q by 4 pi K, where Q is the heat energy. So Q, I can convert it in terms of voltage or current, and then from that slope, I'll back calculate what is my thermal conductivity. So that is what I was doing. So thermal needle probe is nothing but a copper tube. In that copper tube, I have used nichrome as the heating element, and I have inserted that at the center, and it was surrounded by magnesium oxide, so that I can ensure uniform heating on the surface. And this probe, when we want to measure thermal conductivity, we'll embed this probe in the medium of which we want to find the thermal conductivity. And from after dipping it, we'll be applying different voltages using this connectors. And when we apply voltage, this will produce heat. So from the using this thermocouples, I'll be measuring temperature, and then I'll be plotting temperature at different time intervals. So I'll get a graph like this, temperature versus. So this is uh, initial period during heating, and after heating a uniform stage will be there, and once my experiment is over, it will start deviating. So in this straight line portion, if I can take the slope, I can use this S here, and I can find out the thermal conductivity value. So before doing, since we have fabricated this, I can't directly use this. I have to calibrate this one. So here calibration means which is the temperature I should use so that I'll get most accurate results. So for that, I have taken glycerol as the standard medium. Because glycerol, I know its thermal conductivity is already known. And since it is a viscous material, its thermal conductivity won't be changing for a wide range of temperatures. So I have used glycerol as the medium for calibration. And then I have taken the temperature value and then I could find that 15 voltage gives most accurate result. So 15 voltage can be taken as the optimum voltage to be used for for this one, for measuring thermal conductivity. Now, again, to validate my probe readings, I was comparing the readings of this probe with a sophisticated instrument called CETA. So, for CETA analysis and probe for comparison purpose, I was doing this thermal conductivity measurement along the Proctor compaction curve. So, this A to G represents the different water contents along this compaction curve. So different samples, different unbalanced mixtures were taken and they were mixed with a particular amount of water content. If it is A, this will be the water content. And I was aiming at this dry unit weight. So that it will give a standardization. So I can tell if this is the compaction energy, this will be the thermal conductivity. So for that I was doing the thermal conductivity determination along the compaction curve. This table shows the thermal conductivity values obtained for SB30, that means a sand bentonite mixture with 30% bentonite content. A to G represents the water content or the position on the compaction characteristic curve. And here you can see that the thermal conductivity value is increasing as the water content is increasing. So this means that when we add water, there will be a thin film developing around the soil particles that bridges the small gap between the soil particles, and this will ensure more heat flow and thus resulting in more thermal conductivity. So from this graph, the thermal conductivity of values obtained from the probe and that from CTherm. CTherm is a commercial tool was compared, and we can see that both are matching uh, together along the 45-degree line. So this was also revealing the accuracy of my probe. Similarly, different sand bentonite mixtures like SB10, SB30, SB50, SB70, SB100, etc. were tested for their thermal conductivity. And in order to generalize the long-term performance of the buffer material, we need to we need to get a comprehensive understanding of the variability of thermal conductivity for different environmental conditions. So for this purpose, we were comparing the experimentally obtained thermal conductivity with different prediction models available in the literature, and we could observe that there is existing models were there which can predict the thermal conductivity values of sand bentonite mixtures or buffer materials. So this was highlighting the need to develop a generalized prediction model. And for the development of a generalized prediction model, I was using different multiple linear regression based models depending on the for different considering different particles as distributions like sand, silt, clay fractions, and mineralogy like quartz. What is a quartz content? Kyolinite, montmorillonite. So accordingly, different regression analysis were done for different soil samples, the buffer materials, and finally, I could arrive at a multiple linear regression model, which looks like this. And this graph shows the how the model performs. So you can see the model is performing well with a regression value or regression coefficient of 0.95, and the error value is only 0.15. So like that, I could come up with a prediction model for thermal conductivity. This is about the thermal conductivity determination. So next one, another important area in geoenvironmental engineering, other than this buffer material characterization, is a composite liner system. So typical composite liner systems will be using for landfill liners. I hope you have heard about landfill liners. Landfill liners are the uh, dumping yard kind of thing where we will be disposing or dumping our municipal solid waste for a long time, and we'll be contain that from the surrounding geo environment so that the nuisance of this waste won't be coming out. So for this purpose, we'll be using liners at the bottom and top. We'll be using liners so that from the bottom, the contaminated liquid because of the biodegradation won't be coming out, and from the top, hazardous gases like methane won't be coming out because of the biodegradation. For this purpose, we'll be using some protective layers. So this figure shows a double composite liner system where we'll get maximum protection. We'll use double layers of protection layers, which includes a geotextile, a geomembrane, then a geosynthetic clay liners. Then after that, again, that layer will be repeating, and then an attenuation layer will be there. So the purpose of this layer is even if there is a crack, and this leachate will tell that contaminated solution is called as leachate. So even if that leachate comes out, it will not directly come and hit our environment. So after this attenuation layer is our ground or the whatever geo environment will say. So it will not disturb the geo environment. So for this purpose, we have to uh, characterize this attenuation layer and all these components so that we will get a long-term performance for the better service life of this liner. So as I told, from the waste, this leachate will come out and go out to the geo environment. Similarly, for this from this buffer material, from the BGR, even if there is a crack in the canister, this hazardous waste contaminants can come out through the buffer material and disturb the surrounding geo environment or the host rock. Generally, we'll put this deep geological repositories in DGRs will be in host rocks. So for that, we can do several characterization techniques. Here, the most important characteristics will be contaminant transport parameters. So how this contaminants will be transporting from this towards this. So you can see here the waste concentration will be high. Here it will be minimum. So according to the equilibrium conditions, this high concentration will move from here to here so that equilibrium will reach. So according to concentration difference, these contaminants can move out. And this is at high depth, the pressure will be there because we are containing. So there will be a pressure difference. Because of the pressure gradient, this waste materials can come out. So that is called as permeation or advection. And while moving from here, if you are using clay, I was highlighting my bentonite. I got 364 as a liquid limit, and it is highly. I could find it as highly reactive. So one of the advantage with that is it will absorb most of the contaminants. So accordingly, if I can find out the characteristics of contaminant transport properties for different bentonite or sand bentonite mixtures, I can use any existing relation. This is the contaminant transport relation, which will govern the transportation of contaminants in case of liners and buffer materials. So this is called as three-story equation. Here, this is the relation connecting concentration with respect to time and concentration with respect to distance, depending on different coefficients. So these coefficients are mainly diffusion coefficient, advection coefficient, retardation coefficient, absorption coefficient, and in case of radioactive materials, it is the decay constant. So if we can find out all these parameters, we can predict what will be the output or when this my if I am focusing on my liner or I am focusing on my buffer material, until what time my liner or buffer material will be working fine if I know this coefficients. So for that, we have several numerical tools. One of such tool is Pollute, which is the most advanced one, which was developed by Professor Rao, Kerry Rao from Queen's University. So for this one, as I told, this is the KD. KD means a retardation coefficient or sorption coefficient. So as I told, if we are using bentonite clay, it is since it is highly reactive clay, it is charged one, it can absorb most of the contaminants. So we can find out this value using two tests. One is column sorption test and one is batch sorption test. So among these two tests, column sorption test is the most accurate one. The only problem is that in column sorption test, we'll be preparing our liner like this. A small model will be prepared and we'll allow the contaminant to interact with our liner, and then finally we'll collect the effluent coming out through this liner at regular interval of time, and we'll be determining its concentration, and from the concentration difference we can find out what is KD value or the sorption coefficient value. The only problem is that since bentonite is having very less permeability value, we usually we won't get any effluent here for 1 or 2 months. So it may take 2 to 3 years for us to get a good breakthrough curve. We'll call breakthrough curve. Concentration versus time curve is called as breakthrough curve. So you know that mostly one research work, one project work, um, duration is only 3 years. So we can go with that. So for that, for accelerating this kind of testing, we can go for centrifuge testings. So this is the picture showing a geotechnical centrifuge at IIT Madras, which I was using during my doctoral work. And this geotechnical centrifuge have two buckets like this. In this bucket, we can prepare the model and we can put it. So whichever property that is linear dependent, we can measure using this accelerated centrifuge modeling technique. So in this technique, what we'll use is we'll apply n times g acceleration due to gravity. We'll be multiplying this gravity with some constant depending on our prototype and model. So according to this n value, we can set the RPM of this bucket, how it rotates, this RPM of rotation of this bucket, and thus we can accelerate the flow of contaminant and we'll get breakthrough curve. So finally we can back calculate the actual KD value. So using this kind of experiments, we can efficiently demonstrate the behavior of different materials. So another one is numerical modeling. So this one is for numerical modeling of deep geological repository for transport of temperature or heat migration, how the temperature will be varying for a this much period of time. So for that I was using SV heat, a numerical tool called SV heat. It's based on finite element method. So here I was using simulating this. This is a DGR, and I'll be I was using mesh, like finite element analysis uses meshes. So this is the mesh diagram which I observed. I could get it using SV heat, and finally I could simulate what will be the change in temperature. So with that change in temperature, I was finding out these parameters, and using pollute I was expecting long-term I was predicting the long-term performance of the buffer material. So these are some of the research works which we used to carry out in geo-environmental engineering. So coming to the summary and concluding remarks, we were mainly focusing on the characterization. The characterization actually investigates and measures the structure and properties of a material under consideration, without which the scientific understanding of engineering materials could be ascertained. The engineering properties which we need to find out other than conventional technique depends on the uh, application performance which we are expecting during different applications. So accordingly, if experimental setups and apparatus are not there, we can design and fabricate. Only thing is that we should incorporate, the design should be according to an existing principle that governs a basic mechanism involved behind that characteristic. And the developed setups and models demands proper demonstration using accelerated studies or theoretical studies, and we can determine generalized relationships to get the engineering properties that can be utilized for estimating that, and it will be very much helpful to the future researchers. So these are some of the scope of geoenvironmental engineering. I hope you got some idea about the geoenvironmental engineering related research works and all regarding the characterization techniques. With this, I'm coming to the end of my section. Thank you all. If any questions are there, you can share it in the chat box.
Thank you, Miss. So now we can move on to the doubt clearing section. If you have any doubts, you can comment on the YouTube channel itself, okay? Miss, the first
Hello.
question is,
Yeah.
during decorate work, you have to equipments purchasing or fabricated. During decoration work, you have to equipments purchase or fabricated. Which one we have to use?
That depends on our like character, which whatever property we need to find. For me, that thermal characterization techniques equipments were not there, standardized equipments were not there, so that is why I was fabricating. So if you have standardized materials or equipments available, then it will be very much useful if you can go for that, because it will be more reliable. If you're fabricating, you have to prove that this fabricated apparatus is working fine. So that is the problem.
Okay, thank you, Miss. Miss, the next question is, which software is most suitable for geomodeling?
Uh, in case of geo-environmental modeling, for contaminant transport modeling, one of the most suitable one is Pollute, and another one is Flag 3D you can use. So these are the normal, generalized, like common tools which we will use for geo-environmental purposes, mostly for contaminant transport purposes. And for thermal studies also, you can use Flag 3D.
Okay. Okay, thank you, Miss. Hope we covered almost all the relevant questions within the time limit. Thank you so much, Miss. We would like to express our sincere gratitude to Dr. Surya Miss for taking such an excellent webinar and thanking you all for your participation. We will be back with next webinar on 4th June 2020. Follow up our webinar series and let's learn together. Thank you.
Thank you, Rajalakshmi. And before concluding, I'd like to thank the coordinators and the entire team for coordinating such an excellent webinar. Thank you, Shah sir and Prasoon sir, for giving me this opportunity. Thank you so much.